No, it's okay. State University. No, it's okay. Yeah, yeah, yeah. This year, yeah. Okay. Thank you very much for the presentation. Thank you all for the audience. Fortunately, I don't need to thank the organizers. So let me show you my place. I mean, this is the University of the State of Rio de Janeiro. The city of Rio de Janeiro has essentially two topological sectors. I mean, the north and the south. And our university is in the north part. That is, you see, this is not a particle accelerator. This is Maracanã Stadium, where a lot of funny things happen over there. Of course, if you decide to come to visit us, you can choose in which topological sector you prefer to work. I mean, I prefer the south part, that is this. This is Ipanema Beach. Okay, let me show you some of my collaborators with which I talk a lot of ideas. Some of these ideas I will try to explain to you now. Essentially, Eduardo Fralkin from University of Illinois at Urbana-Champaign, Daniel Stariolo from Federal Fluminense, Alejandro Mendoza, that is from Santa Catarina, Múcio Continentino from CBPF, my PhD student, Leonardo Ribeiro, another PhD student, Nate Lopez, that he escaped earlier from here, and Rui Aquino, that it should be over there. Yeah. And then we have all the collaborations with Steve Kivelson from Stanford, my friend Luis Soxman, also from UFI, and Daniel Reyes from IME, Instituto Militar de Engenharia. Okay, so I mean, I would like to talk about a very recent work that we've done in collaboration with Eduardo Fralkin and Leonardo Ribeiro. But in fact, it's quite technical work. So I would like to spend most of my talk talking about the motivations. I mean, why we decided to do this work. I mean, why to make bosonization and why to try weak magnetic fields. I will try to show what does it mean weak. I mean, and so we first, I will give you a brief idea of what is nematicity or what does it mean the electronematic phase or the fermion-nematic phase, and how to detect Fermi surface in this state, essentially through experiments on quantum oscillations. And I mean, these are essentially the motivations. I mean, I decided to focus my talk on questions and not on answers, just because I have no answers. So I prefer to make questions. This is more interesting. So let me begin by the beginning. I mean, what is nematicity, or what we understand by nematicity? And the nematic phase is a phase of matter that spontaneously break rotation invariant, but keep translation invariant. I mean, it's like an isotropic liquid. And but the order parameter is not a vector, because, for instance, the magnetization is a vector also do this. I mean, breaks rotation invariance, however, keeps translation invariant. However, the magnetization is a vector, so it's different if you point, for instance, up or down. The nematic phase is different, have a direction, but not, I mean, if you make a rotation of pi, it's the same state. So it's not a vector. You can think as a headless vector. Indeed, it's a tensor. It's a symmetric traceless tensor. This is the order parameter. So it's an order that is different from magnetization. And okay, uh, I mean, there are a lot of evidence, experimental evidence of this phase in very, very different systems, essentially strongly correlated systems. Of course, the classical part is very well known and are just liquid crystals. I mean, but what I would like to tell you about is the quantum nematic phase. I mean, a nematic phase that is realized in electronic systems. And one of the first systems was two-dimensional electron gases. When you feel the Landau levels, higher Landau levels at half filling. I mean, there you see huge anisotropies in the transport. I mean, in the Hall conductivity or even in the longitudinal conductivity, and the temperature dependence of this anisotropy is essentially like a phase transition, like a second-order phase transition. This is then you have this type of compounds, strontium rutenate, essentially heavy fermion systems that when you have a metamagnetic phase transition, and there you can see also doing transport near this metamagnetic quantum critical point, you see a deformation of the Fermi surface that breaks rotation invariance, keeping translation. And this is also called a nematic phase. In the cuprates, this is just an example, but in most of the cuprates, you also see or interpret at least this phase using different types of experimental techniques. For instance, you see an isotropy in the resistance. You can do neutron scattering. You see an isotopy in the magnetic response. Also in the Nernst effects, and well, one of the last experiments is using Josephson tunnel microscopy, that when you can see this type of anisotropies in the density in the responses. Okay. So, well, I put here this picture, this draw, I mean, of the phase diagram of cuprates. I mean, in this workshop, many people show this, and just to show you that what we expect to see or to develop this electronic nematic phase in this region. However, there are a lot of phases related with the nematic phase when you combine nematics with superconductors. I mean, we expect here in the pseudo gap phase that here says charge density wave, but there are a lot of data that are suggesting that you have a mixture of superconducting bubbles in the middle of this nematic background. We call it nematic superconductor. But in this talk, I won't not talk about this phase, but we have worked a lot in this type of phase. Okay, so the point is, again, what of questions I would like to answer, and I mean, I'm bothered with quantum criticality. So what about the isotropic nematic quantum phase transition? I mean, if it exists, I mean, how we can describe it theoretically, and and the other questions that is related with that phase diagram is what about competing orders? I mean, competing orders between, for instance, nematic and superconductors and all charge density wave or magnetic order. I mean, okay, but in this talk, I will talk about this first question that you can find in these two papers. So let me talk about how we understand the isotropic or the nematic phase transition. You have two ways to do that. I mean, you can begin with, for instance, what we call a symmetric phase or a striped phase. That is essentially, the black lines are high density sectors and the white ones are low density sectors. So you have like a charge density wave or something like that. And if you put defects in this structure, these effects are essentially dislocations. Dislocations try to, recover translation invariance that is broken in this state, but you remember, one of the directions. So this is one picture, of this nematic phase. Yeah, Daniel. Yeah. Another way to see or to understand this type of breakdown of the rotational symmetry, if you begin, for instance, with the isotropic Fermi liquid, and you break the symmetry, deforming the Fermi surface, and this is done through a Pomeranchuk stability that I will talk about a bit about this instability. But again, if you see this type of phase transition, you are breaking again rotation invariance, keeping translation invariance. And you see that, for instance, this point of the Fermi surface is essentially the same of this one. For this, you have the nematic symmetry. If you change any vector by pi, you get the same. Okay. So, what is a Pomeranchuk stability? This is an old issue. From Pomeranchuk in the 50s. This has to do with Landau theory of Fermi liquids. The point is that if you excite your system, we begin with some Fermi surface and you deform this Fermi surface. If you compute, for instance, the energy that you need to deform the Fermi surface using Landau Fermi liquid, you will see that it's essentially a bunch of harmonic oscillators that you have. The energy that you need to pay, depending on the deformation of the channel that you are deforming on the symmetry, essentially has the form of harmonic oscillators, where the frequency has to do with the interactions. These F are the Landau parameters that codifies the interactions in the system. Well, this is standard. The problem is that if in some channel the interaction is sufficiently attractive, this F is negative, you can have a channel, an unstable channel, when you have an inverted oscillator. And if this happens, your Fermi surface blow up. Fermi surface doesn't blow up. What with blowing up is your theory. But what can imagine that what's happening, that you get a permanent deformation of the Fermi surface, and the form, this depends in what channel of angular momentum that you are breaking the symmetry. For instance, this is what we call the isotropic nematic transition, and it's related with F2, that is essentially the symmetry is cosine of 2 theta. There's an ellipse. For instance, if you take a Pomeranchuk stability in this channel, F6, you have what we have an exotic instability, that the residual symmetry is to change the angle by pi over 3, essentially. This is the physics of the instability. The new thing is how you can interpret this in the sense of a real phase transition. This is just an instability of the Landau theory that is quadratic. Okay. We studied this type of transitions for a long time. Again, which are the questions that we do about this transition? The static properties of the order parameter are dictated just by symmetry. So these properties are very similar with the classical theory. It has nothing to do with quantum theory. You can develop a Landau theory for the phase transition and do it. The difference is the the dynamic part. I mean, the quantum dynamics of the order parameter is that you don't know. I mean, because quantum dynamics come from microscopy. So, try to figure out which is the quantum dynamic of the order parameter beginning from microscopy is an open question. This is the hard part of the story. And the other harder point is what happened with the fermions when you are at this quantum critical point. And this is a general question. I mean, nobody knows what happened with fermions at any quantum critical point. I mean, this is just one example of a critical point. Okay, so we try to answer some of these questions just looking at a model. I mean, it's a simple, very simple model. And it's a very old work that we made with Louis Oxman. We just look for for the simplest Hamiltonian that you can imagine. I mean, this is essentially spinless fermions. This is the quadratic part with some dispersion, and you plug, two-body four-way scattering interaction. I mean, the most general four-way scattering that you can imagine. This F here that depends on 2 points on the Fermi surface and some Q are codifying essentially a general four-way scattering two-body interaction. And the energy dispersion, we essentially expand in the Taylor series very, very, very near the Fermi surface, because what we are interested is what are the excitations very, very in the strip very near the Fermi surface. Yeah. Yeah, short range, yeah. Okay, so the point is, well, what happened? I mean, how we can analyze this model, and the point is that to reach a phase transition, we need a non-perturbative techniques. I mean, if I make perturbation theory in some F, I can't see any phase transition, so you need a non-perturbative one, and for this reason, we choose bosonization, and this is one of the first questions, why you need to use bosonization. And, well, this is a two-dimensional model, so we would like to make bosonizations in 2 dimensions, and this is a problem. I mean, most of you know that bosonization is a very good technique in 1 dimension. This is an exact technique in 1 dimension, but not in 2 or 3 dimensions. And, I mean, multidimensional bosonization has a long story. Began with Luther in the 70s, and then was developed more rigorously by Antonio Castroneto and Eduardo Fradkin. This is essentially, this transparency is the doctoral thesis of Antonio. At the same time, you have works by Houghton and Marston, and then Haldane in '94. I mean, there are a lot of works around that, but this, from my point of view, this is the principal works where the technique is set up. And what does it mean? I mean, what we do in order to make this technique? I mean, the principle, I mean, the basic point is that, well, we have a Fermi surface. I'm making an example with a circular Fermi surface, but we can do it with any form of a Fermi surface, continuous. I mean, this technique doesn't work if you have vertices like, because the density of a state in a vertex is not well defined. But so what you need, you need to begin with a smooth Fermi surface. I mean, any form. Then, and you are interested in the dynamics very, very near this Fermi surface. I mean, very, very low temperatures, essentially 0 temperatures or very, very, very small temperature. So you essentially put a cutoff very near the Fermi surface, and you divided this Fermi surface in patches. I mean, and inside this patch, so you have these 2 cutoffs just defining a patch, and inside this patch, you essentially have a 1-dimensional system. So the idea is to bosonize in one dimension, that we know how to do that, and then sum up all the patches. And this is the difficult part. I mean, you need to recover all the Fermi surface. So you can define, for instance, fermions, this phi s at each patch of the Fermi surface, and then you recover the complete fermion operator just summing up over all the Fermi surface. This is essentially the same that in one dimension you have right movers and left movers. But here you have, I mean, here you have not right and left. I mean, you have just a lot of patches that we label by this letter here, S. And, okay, and what are the bosons? I mean, what does it mean, bosonization? I mean, we just express fermions in terms of bosons, but these bosons are essentially particle-hole excitations in each patch. I mean, very, very, very near the Fermi surface. So this delta n here represents a particle-hole excitation in each patch of the Fermi surface. And okay, you can compute, for instance, from microscopy, I mean, from the fermionic part of the theory, you can compute the commutator of this bosonic excitation, that densities, and you find this algebra. I mean, you can close this algebra, and you get this this part that is the chiral anomaly of a Schwinger algebra. Yeah. Excuse me? No, this is not an answer. This is approximation. I mean, this is not exact. I mean, I am making here an expansion, and in what? In essentially lambda, that is this cutoff over this lambda, this is small lambda. I mean, this is exact when you when the cutoff go to 0. When you are exact. Excuse me? Yeah, okay. I don't understand your question. No, in the patch itself, no. But I will recover Landau damping when we sum over all the patches. I will show you that, yeah. Okay, the point is that you can solve this algebra in terms of canonical oscillators, essentially. You define this field here, phi, you compute the canonical momentum, and the commutators are essentially usual. I mean, you have a bunch of chiral bosonic fields at each patch. Okay, this is essentially the essence of bosonization in 2 dimensions. You can do it in 3 dimensions also. And I mean, the physical interpretation of this is that this field is essentially a deformation of the Fermi point. I mean, you begin with some Fermi point, and this is a local deformation. So this field is parameterizing a coherent state of deformations, I mean, in all the Fermi surface. And well, of course, we can go through this type of technique, and you can rewrite that model that I show you in I mean, as a field theory in terms of this bosons here, phi. This is essentially the free part that you see that are, I mean, each S represent one patch, and for each S you have essentially chiral excitations, I mean chiral bosonic field, and this is the interaction part. That the funny thing is, well, the same way that in bosonization in 1 dimension, this theory is quadratic, so you can solve it. Of course, it's complex because you have a bunch of harmonic oscillators all coupled. Okay, but it's quadratic, so in principle, you can diagonalize all this and compute the spectrum and all that. Okay, we did that. Okay, we did that in a model of the isotropic nematic transition. What do we do? No, it's short range. We put a delta or very, 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 very short range. Yeah, no, it's very short range. So, what do, yeah. No, all. No, all. No, no. No, the points of the Fermi surface are here in ST, and I am summing of all the Fermi surface. Yeah. Well, when you are away from the critical point, we don't know what happened at the critical point, or at yeah. I mean, if this F is repulsive, it's Landau theory. Yeah, it's exactly. But here you can approach the critical point, and this is what we do. I mean, put. Yeah, exactly. This is the. Exactly. Yeah. This point. Yes. 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 Like backscattering, something like that. You are saying no. I not take into account that. I mean, these are another operators that I can put in the theory. But no. This is okay. No, this is the model of force-cutting interaction. Just that. But I can. But this is not fundamental. I mean, I can put these operators and try to make some romanization group and see if they are relevant or not. I mean, I can do that. Yeah. No, this is the simplest model. I mean, forward cutting interaction. So this is. I mean, the momentum is Q. I mean, it's very, very, very small. Okay. What we did is to take for this F just a model, just take F2. I mean the channel of L equal 2. That is, we know that it will produce an ellipse in the. I mean, if you have some instability, you will have an ellipse in the Fermi surface, and we compute the action at the critical point. I mean, what we found is this. I mean, this value is exactly when you have the quantum critical point, and this M2 is the quadrupolar momentum. That this is essentially the bosons in this critical point and are quadrupolar moments essentially, and the dispersion is, I mean, it's a strange dispersion because it's cubic and is imaginary. I mean, you have dispersion that we associate this with Landau damping, and it's very, very smooth. It's like a phonon, but very, very, very soft phonon. I mean, so, I mean, the low energy physics of this transition of this critical point is dominated by this type of dispersion. So 3 is essentially the dynamical exponent. So the effective dimension is 5. So it's higher than the upper critical dimension. So we are safe that any calculation at mean field is at least, well, it's exact if you compute the exponents. The interesting thing is if you go to the order phase, I mean, you pass through the critical point, you have this deformation. I mean, you break your symmetry, and of course, well, in the continuum you will have Gaussian modes, and the Gaussian modes are essentially, I mean, oscillations of this ellipse because you don't need any energy in order to rotate this energy, and the dispersion of this Gaussian mode is exactly the same. I mean, it's so it's not really a quantum critical point. It's a quantum line. I mean, because the nematic phase itself is critical. I mean, so this is not usual quantum critical point that when you have an ordered phase and disordered phase. I mean, you have a point that is separating a disordered one and a critical line. Critical line in the coupling constant. I mean, in this F. Yeah. No, I don't know. No, there are a lot of questions that in order to understand here, but no, we don't know what happened there. What we try to compute is what happened with the fermions at this point. And yeah, at the mean field exponent. No, along the line. No, at the critical one. Yeah, at the critical at the classical one with the Z. I mean, just scaling with Z equal 3. I mean, this is so. We try to compute fermionic correlation functions, and of course, you need to map fermions into bosons. So you have this mapping here. The fermion in each patch, I mean, is an exponential of these bosons, and remember that these bosons are parameterizing the deformation, I mean, of the density of the Fermi surface, and essentially you can compute using the algebra that I show you the fermionic green function that is essentially the free function multiplied by certain function z. That is essentially the wave function normalization. Well, we compute this. Well, this z is quite hard to compute at the critical point. We could compute in some cases, for instance, the autocorrelation. If you put t equals 0, for instance, and compute for x, for large x, and you see that you have a function that decays as x to the 1/3. And this is quite strange. I mean, because, it's not a gap, because this is a possibility that when you have a phase transition, the system opens a gap, and you have an insulator or something like that. But if you have a gap, what you expect is an exponential, e to the minus x. However, in the latential liquid is a power law, and this is in the middle. I mean, this is not an exponential, but it's not a power law. I mean, this is something strange. And well, we identify this with some anisotropic non-Fermi liquid. I mean, this is not a Fermi liquid. However, we don't know what it is. I mean, yeah. Here? No. No. It's just the gradient of the field. Yeah. Okay. So, we have a lot of work around this, but this is essentially what we know about this critical point. I mean, what we would like to do, and we are trying to do we tried to do for 10 years, and we didn't get, is to make a fermionic normalization group in order to compute anomalous dimensions. We don't know how to do that, but we are trying. Okay, but let me move to the other point with a very recent work, is that we try to put magnetic field in this theory. But first, let me explain you why. And the point is that the Fermi surface is, it's an intellectual construction. I mean, the point is, what do we know about the Fermi surface? I mean, from experimental point of view. And to the best of my knowledge, you have two techniques in order to see the Fermi surface. And one is quantum oscillations, and the other is to look for spectral functions essentially in angle-resolved photoemission. And so let me talk about a bit what are quantum oscillations, and it's a very popular technique in order to reconstruct or to see or to picture Fermi surface. And quantum oscillations, essentially, I mean, you put a magnetic field in the system, in any system. So you have essentially a quantization of the spectrum. I mean, you have Landau levels. And if you compute the density of a state very, very near the Fermi surface, you have this type of features in terms of the energy. I mean, when the energy crosses a Landau level, so you have a divergence here. You have a periodic feature. And of course, any observable that depends on the density of a state will oscillate with the magnetic field. This is a quantum oscillation, essentially. In particular, the magnetization oscillates with this function, I mean, 1 over b, and the period of this function is proportional to the Fermi surface area. And this is why we can get information about the Fermi surface, because what people do is essentially take your sample, put your magnetic field, look for the oscillations, and measure the period, and change the orientation of the magnetic field, so you have information about the areas of the magnetic of the surface, and try to reconstruct with just holographic technique the Fermi surface. And these are the beautiful pictures that you see in the papers. But the point is that this relation between oscillation and the geometry or the topology of the Fermi surface, the basic theory that you have is called the Lifshitz-Kosevic theory, and it's free fermions. I mean, it's essentially a gas, or at least a Fermi liquid, and you put a magnetic field and compute the magnetization, just that. And from that, you take this relation between oscillations and geometry. And of course, this technique worked very well for normal methods. I mean, indeed, this is from the 50s. I mean, from the 50s, people used to measure Fermi surface in that way, I mean, in normal method. The problem is that, these oscillations you can observe in highly correlated systems very, very near quantum critical points, that you know that you have anything but free fermions there. And this is our question. I mean, how can we say something about Fermi surface just using a free fermion theory when you are very, very near quantum critical point? And these are just two examples. I mean, this is an example of cuprate. It's an experiment measuring resistivity in terms of 1 over b, and you see oscillations, and from these oscillations you can recover the form of the Fermi surface. The other one is from the group of Santiago. It's essentially what we call the Haas-van Alphen effect. That is, you measure. Well, this picture is the magnetic susceptibility in terms of the magnetic field. So you see that here we have something like a phase transition. They call it metamagnetic phase transition. But here, before and after the phase transition, you have this feature, these oscillations, that they interpret like quantum oscillations. And from these oscillations, they recover the Fermi surface. So they are indications that of the existence of a Fermi surface. However, they are very, very near quantum critical point. So I talk a lot with experimentalists how they do that. And the question is simple. We have a black box with a Lifshitz-Kosevic in there. We apply it and make the draws. If you have another black box, give me, and I will use it. Okay, so this is our question. I mean, I would like to build a black box to sell to the experimentalists, because there are a lot of ones, so it's a big market. Well, this is the problem. I mean, how can I build that black box? And okay, again, I mean, the point is that there, to the best of my knowledge, there are no control non-perturbative technique in order to compute quantum oscillations at a quantum critical point, or very near. So our proposal is to use bosonization, but you need to plug a magnetic field in this technique. And what we did in that last paper that I'm trying to sell you is that is how we could put weak magnetic field in the system. And weak magnetic field means that in each patch of the Fermi surface you have huge Landau levels. I mean, the system is always very near Fermi liquid. I mean, if you put a strong magnetic field, what you have is a huge gap. You don't have any Fermi surface, and you have quantum Hall effect and all that, all type of phenomenology. This is the other regime when the magnetic field is so small that you have essentially a continuum. I mean, teeny gaps around the Fermi surface, so you can still talk about Fermi surfaces. And this is the regime of the quantum oscillations, when you need to see quantum oscillations. And okay, the hard part of the bosonizations is the free part and not the interaction part. Because if you have four-way scattering interaction, it's very, very simple to make bosonization. What you don't know is how to bosonize the free fermions. I mean, this is technically is a hard part. And okay, so let me take a very, very simple model, just fermions in a magnetic field. I mean, in an external magnetic field. And again, we project this Hamiltonian in this patch of the Fermi surface. So you have a fermionic Hamiltonian that essentially are chiral fermions, with the difference that here, this D now is a covariant derivative, where you have essentially a gradient. And you have this term that you see is essentially a derivative in the Fermi momentum. And this is what, I mean, you have a bunch of chiral fermions coupled with this derivative that makes the fermion essentially wrap around the Fermi surface. Yeah. 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 We are working with spin and with Vary phases and with that, but these are spinless. Yeah. Yeah. It's uniform. Yeah. He wrote the covariant derivatives. Yes, yeah, he wrote the algebra, but nobody knows how he computed, and probably he didn't compute it. I mean, he's a very clever person and wrote the algebra, but there's nothing done with this algebra. Yeah, you are right. This paper of Haldane, that paper in '94, yes, but you know. You don't think what? No, it didn't. Okay. Okay, this is the algebra you are talking about. I mean, essentially, again, you compute this particle Hall excitation, compute the algebra, and you have essentially the same algebra. I mean, the same Schwinger algebra, but now is covariant Schwinger algebra, because this D is essentially a covariant derivative. The difference with Haldane, as we did compute it. I mean, from so the point is that the difference with the other bosonization without magnetic field is that when you try to build up the fermionic operator in terms of bosons, you see that the relation between bosons and the deformation of the Fermi surface is through this covariant derivative. So if you invert this, you see that the bosonic field is given by a coherent superposition of bosons, and where where the width of this superposition, the weight of this superposition is essentially the green function of the covariant derivative. So it's not local. I mean, in order to define a fermion in one patch, I mean, the contribution to the fermionic operator in one patch are bosons all around the Fermi surface and not in one patch. I mean, you have, I mean, it's more complex structure. Because just what the magnetic field is doing is wrapping the bosons all around the Fermi surface. I mean, you cannot isolate this patch. The magnetic field are connecting all the patches. Essentially, this is what is happening here. And well, then that you have the technique, you can bosonize in principle any Hamiltonian, at least four-way scattering. And you see that the free part, I mean, of the fermionic theory is mapped into a quadratic bosonic theory. And well, here is just one example of interaction with F0 that is quartic in the fermions. You can bosonize again into quadratic terms of bosons, and the magnetic field enters through this algebra, essentially that. And again, you have a quadratic theory, more complex, but you have a quadratic theory in order to diagonalize. Yeah, just one example. Yeah, just one example. So this, how is it useful or not? I mean, this is just, as I said at the beginning, quite technical. I mean, we just make the tools in order to compute, but what in fact we can compute with that. And so we tried, okay. Look that here, it seems that you don't have Landau levels. I mean, or the Landau levels are hidden in the formalism. The Landau levels appear if you try to compute the green function of the covariant derivative. When you try to compute this function, you put periodic conditions on the Fermi surface, you get, this is the green function, and you see that have poles each time omega cross the Landau level. So the Landau levels are hidden in the inverse of the covariant derivative. And okay, what we did is to compute the magnetization in order to try to see if we are able to compute quantum oscillations. And we did it. I mean, we compute the magnetization of this model, and you recover the 2D Lifshitz-Koszewicz formula for at least for t equals 0 when you can see this type of oscillations. I mean, far away from the critical point, of course. I mean, there's no, but at least we can recover all the, I mean, the black box of the actual black box. I mean, well, we compute another things like collective mode just to be sure that the technique is working. I mean, for instance, we compute corrections to the Landau zero sum. You see that this is collected mode. I mean, omega over q. This result is essentially the classical result of Landau. I mean, without field, without magnetic field. And this is the correction, and you can see that. Well, these are results from this. This is omega in terms of q. I mean, the dispersion of the mode. This straight line is the result of Landau, and when you put a small magnetic field, you get these oscillations that again are quantum oscillations of the interacting system. I mean. Yeah. We didn't, but we are thinking this type of, at least, I mean, we are trying to compute all without impurities. But if you want to compute some transport, we need to put impurities in this, yeah. Yeah, we are trying to do that right now. Yeah, yeah, yeah. You have a very phase around. Well, it depends if you have spin orbit coupling or not. I mean, it's tricky. Okay, the point is, okay, this is working, and what we are thinking about. I mean, what we are trying to do is to approach the isotropic nematic quantum critical point. I mean, we are trying to compute quantum oscillations and that phase transitions. To do that, we need to plug a Hamiltonian, I mean, an interacting Hamiltonian that is a bit, it's more complex. It's essentially, this Q is the nematic order parameter, so this is typically the interacting part of the interacting Hamiltonian of two quadrupoles. And the difficult thing is that this Q is defined in this form in terms of fermions, and you have the covariant derivative here. So in the definition of the quadruple, the quadruple don't couple with the magnetic field in a minimum way. I mean, you have these interactions between magnetic field and the fermions that is not trivial to work out. But in principle, this is quadratic, so we can do that. We are trying to bosonize this and compute quantum oscillations. I mean, trying to compute the magnetization and then try to tune the quantum critical points. We are doing this right now, and we hope to report on this soon. Okay, so just to resume, I mean, we have characterized the isotropic nematic transition. I mean, without magnetic field, we compute the exponents, and we saw that this is not a Fermi liquid. It's a very very strange thing, and then we generalized the bosonization technique to consider a very weak magnetic field in order to compute oscillation. This is essentially the work. And the point is, okay, again, which is the fate of fermions near the quantum critical point. This is how to build up a fermionic normalization group. We don't have to do that, but we are trying to do it. And the more practical thing for me is to try to compute quantum oscillation, the Haas-van Alphen or transport properties near or at a quantum critical point. I think that this is important just because we will have that black box for the experimentalists. So, okay, this is the work. So thank you very much for the attention.